Okay, so I recently picked up a couple Raspberry Pi Picos. Finally, I know I'm a few months behind on that. And well, there's if you're watching this video labeled with something about Picos, then you're probably well aware of the speed that comes with these and all the functionality. Some very nice features. I'm really loving the board. Um, the only thing I don't like about this is somebody decided the labels should be on the bottom, which means when the board's plugged up, we can't read the labels. That seems really odd to me. But otherwise, I'm really loving the board. But like I just mentioned, there's that great speed that comes with it. It's so much faster than most of what we're used to in the little dev boards of this size. And that's what I wanted to address here, real quick, because I'm going to assume people have heard the phrase, there's no such thing as a free lunch. And that is very true in this case because we get a lot of speed, but that comes at a cost. So I wanted to look at that. So I'm going to plug the same circuit up on two dev boards. So for comparison, I've got it plugged up here first using the Texas Instruments MSP 430. Well, it's in the launch pad, but really the microcontroller is just the chip, right? So the and this one the chip pops right out and it goes in the breadboard. That's what we usually do with those, and then this really just becomes a flash, sort of a flash programmer. But I've got it running in here as a normal dev board. Uh, Nothing too fancy going on here. This is my normal test setup anymore. I've got a potentiometer, well, four LEDs, a couple of them flashing, then the potentiometers hooked up to the green one here, it looks like. So analog read from the potentiometer to PWM right on the green LED, flashing back and forth between the blue and the yellow, and then interrupts over here on this capacitive touch sensor, which I use this instead of a momentary button for videos because you can see there's a little light there so you can tell when I'm touching it, and it's hidden behind the wires, but when I touch it, you can see the interrupt kicks on. Everything's running really good, reliably. So let's look at the this same circuit on the Pico, and yeah, same timing and everything as far as the final output. Uh, but there is, like I was going to say, the point here is the cost that comes with that speed. So then we'll jump over and look at the code. So I'll hook this up on, I'll switch out the wires for the Pico, and then we'll look at the code for uh, the code and the um, output that I wanted to make a note of. Because, yeah, that speed does come at a cost. And so here's that same thing running on the Pico. Well, essentially, when I did shot the video for the first one, I forgot the built-in LED on the board, but I did notice it before filming the part for going over the code and what this video is actually about. So when we get to the screen part, the LED on that TI board, the built-in LED there was blinking as well for the results we see on the screen. But the same circuit, got the potentiometer doing the yellow LED this time. It might have been doing the other one the last time, and the interrupts flashing the red light on and off. Uh, those are flashing back and forth every 777 milliseconds, and this one's flashing every 330. No, this one's flashing every 777, and these two are flashing every 333 milliseconds. So let's jump over to the screen now. Look at the code for um, both of these little setups and make the actual comparison because this is uh, this is a much faster chip, but that speed comes at a cost. Okay, so here's the code running on the MSP 430 G2553. I'm using Code Composer Studio Online, which I hadn't used in a couple years. And when I opened it up this summer, Texas Instruments apparently added Energia to the Code Composer Studio, which means we can write with the nice, easy to use Arduino libraries here. So that's what I did. Going with the easy to use. The comparison is going to be in Python, so just figured go with the easy ones. So I set up some pins. So the capacitive touch sensor and the potentiometer, the 4 LEDs and the built-in LED, which I'd forgot a line in the code when I shot the intro scene, so the built-in LED wasn't flashing, but it is now. Some booleans to keep track of what's flashing and what's not, and the last time, just a couple timestamps, last flash, last time, last board, the last time that happened. That way I don't have to use sleep. I can just check the milliseconds or microseconds since then. Set up all the normal setup, and yeah, this line I forgot to put this line in when I shot the video for the little intro section, but I guess you'll just have to take my word for it that green LED on the board is flashing now. Then grab the last timestamp. So each time through the loop, it checks how long it took to get all the way around the loop in microseconds. Then that gives us the period, and its frequency is the reciprocal of period, and it's in microseconds, so times 1,000,000 to get back to just regular hertz. And print that out to the serial monitor. Then the built-in LED is going to flash toggle every 777 milliseconds. So it really just switches that boolean when it's been long enough, then resets the timer, then checks that boolean to write that high or low. Same thing with flashing between the blue and the yellow. If it's been long enough, it just flips the boolean, resets the timer. Now we don't have to use the sleep. Don't have to put anything to sleep, but keep processing the whole time. And then read the potentiometer, remap that, and output that to the analog write. And to control how bright the red LED is. And then down here at the bottom is the interrupt so when the touch sensors click, the green LED immediately toggles on and off. So that's the code. So if we upload that real quick, which I think I got my pins backwards because the red LED is the one being interrupted and the green LED is going to the PWM. So I must have got a wire backwards. But the logic's still the same, and we can still check this, do the test. So if I hit run, just the labels are a little off. Build it pretty quick. Flash it to the board. Shouldn't take too long. There it goes. And now I can open up the serial monitor, which for some reason lately on the CCS Online takes 2 tries to open it. Oh, it opened the first try there. So there we can see how many milliseconds it took to get around the loop and our frequency. So let's look at the frequency here. Obviously the Pico is going to be a lot quicker than this because we have that speed. But what I wanted to point out is the discrepancy here. So if you look at that, it looks like we're varying between 45 and 46 hertz. And, well, it's kind of slow when we rattle off machine numbers these days, but I'm flashing things at 777 or 333 milliseconds, so it's plenty fast enough for that. So it's running there, but we're getting a discrepancy of really less than 1 hertz, but I'm going to round that and just look at the integer part and say it's a discrepancy of 1 hertz. So now let's go look at the same code over on the Pico. Okay, so here's the code for the Raspberry Pi Pico. Essentially the same logic as the previous time, so import a couple libraries, machine in UTime, and I just did the import all to make it a little easier to look at. So set up the LED on the board and something measuring milliseconds. The UTime module has, I don't like to put things to sleep, so instead of using the utime.sleep, I like to use utime.ticks_ms or for milliseconds, or ticks_us for microseconds. And that way the board never actually stops doing stuff. And then just set up the LEDs as output pins and set up the interrupt, put that on one of the pins, the analog read on one of the pins, Boolean to keep track of when things are flashing, and the time. So the same logic. If the difference between the ticks, again, this is built into the UTime library. It's also in the regular time library, but the reference material said for the Pico said use UTime instead of time. And I haven't looked in detail at what the difference is, but they have all the same methods. So the difference between the current milliseconds and the last time it was measured, which if it flashes, if it hits that criteria, it resets the counter and just toggles the built-in LED, or on this other timer, once it's exceeded that threshold, it flops the Boolean and then toggles back and forth between the green and blue LEDs, resets the timer. Read in the potentiometer, which for some reason doesn't go all the way to 0. There was also another problem with the high end that was an electrical issue that I did another video going over that. And then write the reading from the potentiometer onto one of the LEDs. So the same logic. Let me uncomment this, and then, well, I guess this is different because last time I did this at the beginning. This time I'm doing it at the end of the loop, but beginning into the loop, there's not really much time there, much difference there. So I'll hit Alt-4 to uncomment that. I guess to make the logic exactly the same, I should move this line up here. So we get the period, the difference between the current microseconds and the last time it was measured, then immediately take a measurement because printing to the serial monitor is going to slow things, so it's probably going to check it here. And that's microseconds, so the reciprocal of the period is the frequency, and multiply it by 1,000,000 to get up to regular hertz. So if I run this, it goes very, very quickly, and we can see how many hertz we're getting here. So a lot more speed, but you'll notice those numbers are jumping around quite a bit. And on the TI chip, it was a difference between, I think, 45 and 46. And here it looks like we're somewhere in the hundreds. 154, I saw 120, there's 320. So our variance, it was off by 1 hertz on the same logic, off by 1 hertz on the TI chip is off by as much as several hundred hertz here. So that's the cost of that speed. Obviously, it's a lot faster, and we can do things to make this even faster. I went with default settings, didn't adjust clocks or anything, so we can get more speed out of both of them. And obviously, this one's a lot faster, but there's a lot of wiggle room there. We lose some of our reliability and precision, and that's the cost of the speed. So when putting projects together, keep that in mind. The faster is nice, but if faster is what you're looking for, because as you get faster, you're going to lose a whole lot of reliability and precision. So I just wanted to express that point and show some measurements for it, all on default settings and the easy to use one. Energia on the TI chip and Python on the Pico. And yeah, a discrepancy of 1 hertz variability for the TI MSP 430 G2 553 chip, and looks like we're getting several hundred hertz variability on the Raspberry Pi Pico, the RP2040 chip. So just remember the speed comes at a cost. So whenever you're choosing the right components for a project, make sure you're considering the correct things for that particular project.